incredibly close to the source of your own life. I want you to take a second, literally right now, and just find your pulse. Wrist, neck, wherever.
It's a steady rhythm, hopefully.
Right. And, because it feels like this simple thud thump against your finger, we have this very mechanical, almost up and down image of the heart.
Yeah, the one from the cartoons in elementary school.
Exactly. It squeezes, blood goes out, and relaxes, blood comes in. It feels like simple plumbing.
And that is the classic lies to children version of biology. I mean, it works for a 101 class, but if you actually built a pump that way, just a balloon squeezing vertically, it would fail. It would not be efficient enough to keep you alive for 5 minutes, let alone 80 years.
And that is the gap we are bridging today. We're looking at the heavy hitter of medical texts. Guyton and Hall textbook of medical physiology. Specifically, we're tearing apart Chapter 9 on cardiac muscle.
We're moving past the what and getting deep into the machinery of how. And the reality is that the heart acts less like a squeezing balloon and much more like a wringing towel. It's a twisting electrical marvel.
It operates by rules that are just completely different from any other muscle in your body.
Totally different.
So the mission for this deep dive is to understand that distinct machinery. I think we can break this down into maybe 3 main layers to really get it. We have the architecture, the physical shape and weave.
The hardware?
Then the wiring, how the cells actually talk to each other. And finally, the chemistry, the weird ion exchange that keeps the lights on.
Let's start with the architecture, because even the gross anatomy, the big picture stuff, is often misunderstood.
Yeah. Guyton starts right off by correcting this idea of the heart as a single unit. We say, my heart is beating, singular, but that's not really accurate, is it?
No, technically it should be plural. You have 2 hearts. You have a right heart and a left heart. They're fused together, sure, but they are 2 separate pumps with 2 completely separate jobs.
Okay, so let's distinguish them. The right heart is the smaller partner.
It's the low-pressure system. Its only job is to push blood next door to the lungs to get oxygen. That's the pulmonary circulation. It doesn't need to be huge because the lungs are right there.
Whereas the left heart is the real workhorse.
The left heart is a high-pressure cannon. It has to pump blood to your toes, to your brain against gravity.
Yeah.
Everywhere else. The systemic circulation, that requires just massive force.
And within those 2 pumps, we have the chambers. Atrium on top, ventricle on the bottom. Now, I've always thought of the atrium as just a waiting room for blood, a holding tank.
It's a bit more active than that. Guyton actually calls the atrium a primer pump.
A primer pump.
Think about it. Most blood, maybe 80%, flows into the ventricle passively while the heart is relaxed. Gravity and pressure do the work.
Right.
But the ventricle needs to be completely full to be efficient.
Okay.
So the atrium contracts a split second early. It tops off the tank. It forces that last 20% of blood in, which stretches the ventricle walls.
Like pulling a slingshot back just a little bit further.
Exactly. That stretch primes the muscle to snap back with more power. It's the Frank Starling mechanism. The more you stretch it, the harder it snaps.
Okay, so that's the chambers. But let's get to the visual that actually stopped me in my tracks. It's figure 9:3 in the source. I just assumed muscle fibers in the heart ran vertically, top to bottom.
Or horizontally, to squeeze inward like a belt. That would be the logical way to build a simple pump.
Right. But nature didn't do that. The muscle fibers in your heart spiral.
It looks like a basket weave, doesn't it?
It does.
It's highly sophisticated geometry. You have layers of muscle. The subcardial layer, that's the muscle on the outside, spirals in a leftward direction. But deep inside, the subendocardial layer spirals to the right.
So you have an outer shell twisting one way and an inner shell twisting the other.
Precisely. Opposing spirals.
And this is where that wringing towel analogy comes from.
Yes. Imagine you're holding a wet washcloth. If you just squeeze it between your palms, straight compression, you'll get some water out, but it's still soggy. But if you grab both ends and twist your hands in opposite directions,
You get every single drop.
that is cardiac systole, the contraction. Because of those spirals, when the heart beats, the apex, the pointy bottom, rotates clockwise. The base rotates counterclockwise. It physically wrings the blood out.
Which explains the efficiency. But Guyton mentioned something else that happens because of this twist. It's not just about getting blood out.
It's about getting it back in. The recoil. This is fascinating. We usually think of relaxation diastole as a passive thing, like just letting go of a rubber band.
Yeah.
But in the heart, relaxation is an active process.
The loaded spring concept.
Right. Because you've twisted this muscle under tension, there's potential energy stored in those fibers. As soon as the contraction stops, the heart snaps back. It untwists rapidly.
And that creates a vacuum, a suction.
A powerful suction effect. It literally sucks blood from the atria into the ventricles. It doesn't just wait to fill up, it actively grabs the blood. Without that spiraling and recoil, your heart couldn't fill fast enough during exercise, you'd pass out.
So the geometry itself is a performance enhancer.
It's structure dictating function.
Yeah.
Perfectly.
Okay, so we have a twisting, ringing, sucking pump. That's the hardware. Now we need to talk about the wiring, because you can have the best pump, but if the signal doesn't get to all the parts at once, it's useless.
Right. And this brings us to a huge microscopic difference between your heart and, say, your bicep.
In my bicep, I can choose to use just a little bit of strength. I can pick up a feather, or I can try to curl a dumbbell. I don't have to use the whole muscle.
Exactly. Skeletal muscle is modular. You have individual motor units. You can fire 10% of them or 100%. The fibers are insulated from each other. They mind their own business.
But the heart can't do that. It can't half beat.
No. A half beat is called fibrillation. And that's a medical emergency. The heart has to be all or nothing. And to do that, it creates what's called a syncytium.
Syncytium. It sounds like a sci-fi collective.
It basically is. If you look at the histology figure 9-2 in the text, you see these dark bands crossing the muscle fibers. Those are called intercalated discs.
They look like walls between the cells.
They look like walls, but they're actually doors. At these discs, the cell membranes literally fuse together to form gap junctions. These are channels that connect the inside of one cell directly to the inside of the next.
So they're sharing their internal fluid.
They're sharing ions. And ions are electricity in the body. So these gap junctions have almost zero resistance. An electrical signal just flies right through.
So if one gets excited,
they all get excited instantly. The analogy is a stadium. In skeletal muscle, you'd have to tap each person on the shoulder one by one. Slow.
Inefficient.
But in cardiac muscle, everyone is holding hands. If one person stands up, it yanks the whole row up and it ripples through the whole stadium in milliseconds.
So functionally, the heart isn't millions of cells. It acts like one giant single cell.
That is the definition of a functional syncytium. When one cell fires, they all fire.
But, and Guyton makes a big point of this, it's not just one syncytium. If the whole heart contracted at once, the atria and ventricles would squeeze at the same time.
Which would completely defeat the purpose of that primer pump we talked about. You'd just be pressurizing the blood in place. It wouldn't go anywhere.
You need a firewall.
Exactly. And we have one. We have the atrial syncytium and the ventricular syncytium. And separating them is a layer of fibrous tissue that is an electrical insulator. The signal cannot cross that barrier.
It's a dead end.
Almost. Except for one specific gate, the AV bundle. The signal sweeps through the atria, hits the firewall, and gets funneled into this one narrow pathway. And that pathway is designed to be slow.
It creates a traffic jam on purpose.
A very calculated delay. It holds the signal for just a fraction of a second. That pause gives the atria time to finish contracting and empty into the ventricles. Then the signal's released to the bottom half, and the ventricles fire.
Controlled timing through a structural barrier. Wow.
Without that insulator and that delay, the heart fails as a pump. It's just a quivering mess.
All right, we've got the twist in the syncytium. Now the spark itself. The action potential.
The electrical software.
This is where I finally understood why my heart doesn't twitch like my eyelid does when I've had too much coffee. Skeletal muscle twitches.
Woo!
The heart squeezes. And the graph in the book, figure 9-4, shows this massive difference.
It's all about the shape of the wave. A skeletal muscle signal is a spike, up and down, light and fast. A cardiac signal, it's a plateau. It goes up and it stays up.
Let's put numbers on it. Resting voltage is what, negative 85 millivolts. It spikes to plus 20. In my arm, that whole event is over in a millisecond.
A tiny fraction of a second. But in the ventricle, that high voltage holds for about 0.2 to 0.3 seconds.
Which sounds short, but in the neural world, that is an eternity. It's 15 times longer.
It is. And that plateau is the single most important electrical feature of the heart. It forces the muscle to maintain a long, sustained contraction.
If it was a twitch, it would just jiggle the blood. It wouldn't actually pump it anywhere.
Exactly. So the question is how? How does the heart hold that charge?
Guyton points to two culprits, the channels and the potassium.
Let's simplify the channels. Every muscle has fast sodium channels. They're the ignition. Pop open, sodium rushes in, voltage spikes, boom, phase zero.
Okay, skeletal and cardiac both have that. That's the start of the beat.
Yes. But then the heart brings in its heavy artillery, the L-type calcium channels.
L for long-lasting.
Correct. These are slow channels. They take a while to open, but once they do, they stay open, and they let a massive flood of positive calcium and sodium ions flow into the cell.
And since those ions are positive, they keep the voltage inside the cell high.
They prop the door open. But there's a second trick. Usually, to reset a cell, to relax it, you let potassium out. Potassium carries positive charge out, resetting the balance.
But the heart plays dirty with the potassium.
It traps it. As soon as the action potential starts, the heart membrane actually becomes less permeable to potassium. It basically locks the back door.
So you have calcium flooding in the front and potassium trapped inside with the back door locked.
That creates the plateau. The cell is forced to stay contracted. It's only when those slow calcium channels finally close that the potassium channels snap open, potassium rushes out, and the voltage crashes back down.
And that crash is the relaxation.
Phase 3, repolarization.
Now, there is a life-saving side effect to this long plateau. The text calls it the refractory period.
This is crucial. While the heart is in that plateau, while it's squeezing, it physically cannot be stimulated again. It is refractory.
So let's contextualize that. In my calf muscle, if I send signals fast enough, the twitches can stack on top of each other until the muscle locks up. A cramp. Or tetany.
And tetany is great for holding a heavy box. You want your bicep to lock up. But if your heart went into tetany,
You die.
you would die. A heart in tetany is just squeezed shut. No blood moves. The plateau guarantees that the heart must relax before it can beat again. It enforces the rhythm. Squeeze, relax. Squeeze, relax. You cannot cramp a healthy heart.
That is a brilliant failsafe. It mandates a break between every single rep.
It's just beautiful engineering.
But, and there's always a but in biology, this reliance on calcium channels brings us to the final section, the vulnerability.
The calcium connection, yeah, this is where the heart shows its weakness.
We're talking about excitation-contraction coupling, the fancy term for how electricity turns into movement.
Right. In skeletal muscle, the process is very self-contained. The muscle cell has a big pantry full of calcium stored inside it in the sarcoplasmic reticulum. When the signal hits, it just opens its own pantry.
It's a prepper. It's got its own supplies.
Exactly. But the heart has a tiny pantry. Its sarcoplasmic reticulum is underdeveloped. It doesn't hold enough calcium to cause a full contraction on its own.
So it has to order takeout.
It relies on the extracellular fluid, the blood and fluids surrounding the cells. This happens through something called the T-tubules.
The text describes these. They're like tunnels that run from the outside of the cell deep into the middle.
And in the heart, these T-tubules are massive, 5 times the diameter of the ones in skeletal muscle. They're big pipelines bringing the outside world deep into the cell.
So when the action potential hits, it opens channels in these T-tubules, and calcium from outside rushes in.
And that external calcium is the trigger. It hits receptors on the internal pantry and says, okay, now dump what you have. It's called calcium-induced calcium release.
Which means the heart is totally dependent on the calcium levels in your blood, moment to moment.
Completely dependent. Guyton describes a very stark experiment. If you take a heart and you place it in a calcium-free solution, it stops beating immediately.
Immediate.
Instantly. It might still have an electrical signal, but there is no contraction. The engine disconnects from the wheels. Your arm muscle would still work for a while because it's running on its internal stores.
That feels incredibly fragile for a system that has so many backups to be so vulnerable to one single ion.
It is. The T-tubules even try to compensate. They have these mucopolysaccharides inside them, basically charged sugars that act like a sponge to hold extra calcium right at the doorway. But ultimately, the heart is at the mercy of your blood chemistry.
It really does blur the line between the organ and its environment. The heart isn't just a machine running in isolation. It's a machine that needs to taste the fuel it's pumping.
A machine that tastes its own fuel. That's a great way to put it.
So we've gone from the macro to the micro. We've taken apart the pump. If we had to synthesize this for the listener, what is the headline?
The headline is that the heart is the ultimate example of form-fitting function. First, it's not a squeeze, it's a ring. The opposing spirals of muscle allow it to eject blood and then actively suck it back in.
The twisted towel.
Second, it's a syncytium, a collective that uses delays and insulators, that firewall, to coordinate a complex two-step dance.
The stadium wave with a pause button.
And third, it trades speed for reliability. It uses that electrical plateau and external calcium to ensure every single beat is a long, full, uncramped contraction. It refuses to just twitch. It only commits.
It's that image of the loaded spring that sticks with me. Even when the heart is relaxing, it's doing so with energy, it's recoiling, preparing. It never really turns off.
And think about the resilience needed there, 100,000 times a day, every day. For 80 years, it never stops to repair itself like a sore quad muscle.